Hey folks, looking at class number 59 here. We're just calculating power and energy. I'm going to go through this pretty quick because the calculations are pretty straightforward. So power is the rate at which energy is transformed. So how quickly you're using energy or changing energy. So we have this big long equation on the reference table. It says that power is equal to work over time, power is equal to force times distance over time, or power is equal to force times velocity. Now you can notice here that, let me just see if I can get connected real quick. There we go. So you'll notice here, how did we get from FD over T to FV? Well, you probably know that D over T is velocity. So if you just replace D over T with velocity, there you go. Now, surprisingly, power equals energy or change in energy over time is not on the reference table. And I really don't know why, because that's one of the most common ones used. Maybe it's because you should know that work is equal to change in energy. So if you see work, power equals work over time, you know power equals work, change in energy over time. But I don't know why it doesn't really show you. And we measure power in units of watts, which we read with a capital letter W, and that can definitely be confusing because we also use that for work. So how do you get around the confusion? I always say if you're getting confused, just write the words out. It can really help you out a lot. So just to give you some reference, a horsepower is about 750 watts, and a watt is equal to 1 joule per second. Okay, so 1 joule of energy transformed each second. So working through some questions here, it says here, a car engine supplies 2,000 joules of energy during the 10 seconds it takes to accelerate. The average power developed by the car while it's accelerating, 200 watts, real easy. But the hardest thing is that you need to recognize that the 2,000 watts is energy and power is energy over time. Because again, energy over time is not on the reference table. So you gotta be aware of that. Like this next one here, it says, what is the rate at which work is done? It doesn't tell you that it's looking for power, so you need to kind of understand the definition. Another thing here you'll notice is that it gives you a mass of an object that's brought vertically upward at constant speed. So how do you work with this? We got velocity, so power equals force times velocity. Well, one thing you have to recognize, and we write it here, is that the force required to pick something up is equal to its weight. So the force in this case is m times g, 9.8. We get 343 newtons for the force. Then multiply that by the velocity, and we get 1715 watts. This one here, you're given the power in watts, you're given the weight, which is the force, find V. There we go, 2.76 meters per second. And the last one here is, again, just kind of identifying what you're looking for. You're looking for time. And the tough thing, again, is understanding that the force is equal to the weight of the object. So it's mg. That's what your force is in this case, because that's the force required to pick something up. Work through the math, it comes out to 9.8 seconds. That's really just a coincidence that it's 9.8 seconds. So here's some problems here. How much energy does a 40-watt light bulb use every second? So the power is 40 watts. The change in energies are unknown, and the time is 1 second. Cross multiply, 40 joules. Every minute, same setup. Cross multiply, 2,400 joules. Every hour, same setup. Cross multiply, and we have 144,000 joules. So this is an activity here, finding out how much energy lights use in one room over, I believe it's the course of a school day. So we counted 44 lights in the room and 28 watts each. So we came out to a total of 1,232 watts. And some people are estimating they're about 7 hours in a school day, which is about 25,000 seconds. So our power is 1,232. Our time is 25,000. Plug that into our equation here. We find that the change in energy is about, I think that's 30 million joules. Just to give you an idea of how much energy that is, well, 1 barrel of oil has about 6 billion joules of energy. So we can get about 200 days of power out of a barrel of oil, about a school year. So a couple questions here. So we have Dwayne The Rock Johnson, given his mass, he climbs up to the top of a 5-story building. How much potential energy does he have at the top? MGH, real easy. So how much work did he have to do to get to the top? Well, remember, work equals change in energy. So there's no friction mentioned, no internal energy mentioned, so we don't have to worry about that. And the kinetic energy is the change in kinetic energy. Well, two things. You can either say he started at rest at the bottom and was at rest at the top, so his initial and final velocities are zero, thus his change in kinetic energy is zero. Or if he went up the steps at a constant velocity, his kinetic energy would still be zero, or change in kinetic energy would still be zero. Right, so the work is equal to the change in potential energy in this case. So power equals work over time. He went up there in 27 seconds. He generated 1,085 watts. Is that a reasonable number? Well, remember 750 is a horsepower, so like maybe that's a number that we could achieve. That's ballpark what we could achieve. We'll actually look at that in lab. Just a quick question here. You're given the force that you're picking up. You're given the velocity. Calculate the power. Very straightforward. All right, folks. So not too bad. Just practice these. Make sure identify what equation you need to use, what it's looking for. But overall, pretty straightforward. Watch out for like watts is W and energy is measured in joules and work is measured in joules. Watch out for those things. So that's why this definitely requires a little bit of practice and just becoming familiar with the terms.